We're now going to look at a way of building groups out of other ones. This is going to be motivated by our construction of the groups Z mod NZ. So you'll remember that the group Z mod NZ has elements that we wrote this way: 0 bar, 1 bar, 2 bar, up through n minus 1 bar. They were one of our first examples of groups. And if you recall, we defined the operation on Z mod NZ, addition on Z mod NZ, using addition on Z, which is itself a group. So this is sort of defined using the operation on Z, where we said that if I have an M bar plus an N bar, that's just the equivalence class M plus N bar. And we define this in terms of the equivalence relation of being congruent modulo a number. But we can also use the congruence or the equivalence classes that come from cosets that we talked about last time in Lagrange's theorem to define groups as well. And these kinds of groups are going to be called factor groups. Our original groups Z mod NZ are going to be very specific examples of it, but factor groups are in fact wildly more general than just the groups Z mod NZ. Now, it turns out that in order to define these factor groups, we need a new notion of subgroup. These factor groups are going to be built out of a big group that we start with and a particular subgroup of it. Now, unfortunately, it's not the case that we're going to be able to use just any subgroup we like. We're going to need to use a subgroup that has certain nice symmetrical properties. And the precise property that we need is given a name. It's being called normal, being called a normal subgroup. So let's look at definition 64. Let's let G be a group and H a subgroup of G. We say that H is a normal subgroup of G, and we write H is a normal subgroup of G if the following fact occurs. If for all A and G, the left coset AH is equal to the right coset HA. So notice that we have a slight modification to the subgroup notation for this. Our original subgroup notation was basically just a less than or equal to symbol. Our normal subgroup notation is that symbol, but where we've connected up the ends of the less than part of the symbol to get this little triangle here pointing towards the subgroup. So a subgroup is normal if it satisfies this condition where the left cosets of the subgroup are equal to the right cosets of the subgroup. We've actually already seen an example to show that this equality doesn't always hold. Given some subgroups, the left and right cosets could be different. So being a normal subgroup is a condition that actually means something. Now, what this means practically is the following. Practically, this means that if A is any element of G and H is any element of H, then there exists some H prime in H such that A times H equals H prime times A. So this doesn't require that the elements of H, that the individual elements of the subgroup H commute with all of the elements of G, but it sort of says that the subgroup as a whole commutes with the elements of G. If I take an element A times something in the subgroup H, then that's the same as the something in the subgroup H times A. So it's a little bit of a commutative condition, but it's weaker than actually being commutative or being contained in the center or something like this. So testing whether or not some subgroup is a normal subgroup directly by definition 64 is tedious, but this is the definition that we use because it's the property that we rely on to make the rest of the theory work. In order to see where the next condition is going to come from, which allows us to test whether a subgroup is a normal subgroup or not, let's rearrange this equation slightly. Notice that if we take AH equals H prime A and we multiply on the right by A prime, then we get the equation AHA prime is equal, AHA inverse is equal to H prime. And the only thing that we know about H prime is that it has to belong to H. This is what we're going to use, the idea that AHA prime belongs to H for any element A and any little h in the subgroup H. So lemma 65 is the normal subgroup test. And it says, let G be a group, a subgroup H of G is normal if and only if A inverse is a subset of H for all A in G. Or another way of saying this, which is how we usually apply it, this is saying for any A in G and little h in subgroup H, we have that A little h, A inverse belongs to big H. So, checking this condition, especially the blue one, is a lot more tractable than directly comparing the two cosets. It's not hard to see that the conditions are equivalent. Notice also that we're only checking one direction. We're only checking a containment rather than an equality, but it turns out that that's good enough. As long as you prove that this condition holds for any element A in G, then we get the normal subgroup that we need. So let's see a proof of this. We need to prove an if and only if, so let's first suppose that H is a normal subgroup of G. Now remember, this means that AH equals HA for any element A of G. Suppose H is a normal subgroup of G, and let A be in G. For any little h in big H, there exists an H prime in H such that AH equals H prime A. Hence, we have that AHA inverse equals H prime, which belongs to H. Thus, we have that A times H, A prime, if we look at all of the possible products A little h a prime, where the little h comes from something in H, all of those products belong to big H to begin with, and so we have this subset relationship here. This is basically just what we talked about at the end of the last slide. So now, let's suppose that A inverse is a subset of H for all A in G. Now we have the following chain of subsets. We have that AH is equal to AH times A inverse A. And we know that because A inverse A is just the identity. And if we take a set and multiply it on the right by the identity, take the coset with the identity, then that doesn't change the set at all. We also know that we have associativity when looking at cosets. So we know that if we have AH A inverse A, that's the same as AH A inverse A. These are all things we proved back when we first talked about cosets. Now we can use our hypothesis. Our hypothesis is that AH A inverse is a subset of H. So that tells us that AH A inverse is a subset of H, and so this whole set that we're looking at is a subset of HA. Now, of course, this doesn't quite give us what we want yet, because to show that the subgroup H is normal, we need to show that these two sets are equal. We could go through another argument to show the other inclusion, but I want to show a proof technique that's often useful to make your arguments efficient. What I'm going to do is I'm just going to continue this string of equalities and subset relationships, and I'm going to keep doing the same thing. So I can put an A times A inverse on the left of this set HA, because of course A times A inverse is the identity. And again, we can write this as A times A inverse HA. And the fact is that if we have A inverse HA, this is the same as A inverse H, A inverse inverse. And we have supposed that if I take any element times H times the inverse of that element, that is a subset of H. That's been our hypothesis. Because we assumed that this containment holds for all A in G. So if it holds for A, it also holds for A inverse. So in particular, we get that this is all contained in AH. So now look at what's going on. We have on the very left of this string of equalities and containments, the set AH. And we know that that is a subset of the set HA. But going through again, we have that that whole thing is a subset of the set AH. But because we know that the two sets on the left and right are the same, they're both just AH, that means that all of these subset relationships we had throughout actually have to be equalities. We have that AH equals HA, so that means that H is a normal subgroup of G. And there we go. By the way, this same argument also applies when you're looking at numbers, say. If you have some sort of argument and you say that x is less than or equal to y, is less than or equal to z, is less than or equal to x, this all means that everything in sight has to actually be equal. That's the same sort of principle we're using here with the subset relationship. Okay, so the point is to test whether a subgroup is a normal subgroup, we check this condition here. Let's see some examples. First of all, note that if G is an abelian group, then we have that AH equals HA for all, not even just all subgroups, we have this for all sets H. So in particular, this means every subgroup of G is normal. What this tells us is that the distinguishment between a subgroup and a normal subgroup is only relevant, only makes a difference in non-abelian groups. In abelian groups, every subgroup is normal, which means all the things that we're going to do later that require normal subgroups work with any subgroup of an abelian group, but not necessarily on every subgroup of a non-abelian group. Let's look at another example. Given any group G, not necessarily abelian, we have that the center of G is a normal subgroup of G. Remember that the normal subgroup, the center of G is the set of all elements of G that actually do commute with all the elements, with every element of G. So to show this, we could do the following. We could let A be in G, and let's let little z be in the center, be in Z of G. So now we want to show that A inverse belongs to the center. But we know that Z belongs to the center, and therefore A inverse is equal to A inverse. A times A inverse is the identity, which means we just get Z out of this, which does belong to the center. So that's enough to show that the center is a normal subgroup of G. Given any group, the center of that group is always a normal subgroup of G. All right, let's look at something that's not quite as abstract. Let's look at a specific example. Let's show that the alternating group of degree 3 is a normal subgroup of the symmetric group of degree 3. So let's recall that A3 is the set of all even permutations inside the symmetric group of degree 3. And we also have seen that a cycle is an even permutation if and only if its length is odd. And so we have these permutations inside our alternating group of degree 3. Now, a note here. For any element A that actually belongs to the set H, we have that, or to the subgroup H, we have that AH equals equals HA. Thus, it always suffices to check that AHA inverse is contained in H for elements of A that are in G but not in H. So that's what we're going to do here. So if we look at all of the elements of S3 that are not also elements of SA, we have the transpositions 1, 2, 1, 3, and 2, 3. So what we want to do is we want to show that given any element of this set, any element of S3 that's not part of A3, if we take that element and multiply it by A3 and multiply by the inverse of that element, then we get something that's contained in A3. So we want to show that these three sets are all subsets of A3. So let's go ahead and do that. So we have that A3 is 1, 1, 2, 3, 1, 3, 2. And we also have that the inverse of the cycle 1, 2 is just 1, 2 itself. And so now what we get out of this is we're going to take 1, 2 and multiply it by 1, and then multiply it by 1, 2 on the right. And then we're going to take 1, 2 and multiply it by 1, 2, 3, multiply it by 1, 2 on the right, and then 1, 2 times 1, 3, 2, multiply it by 1, 2 on the right. So we're going to take every element of A3 and multiply it on the left by 1, 2, and on the right by 1, 2 inverse, which is just the cycle 1, 2. And then we will go and check this out. So let's see, if we have 1, 2 times the identity, that's just going to be 1, 2. 1, 2 times 1, 2 is just 1. And now here we have a product of 3 cycles, and so we can take their product as normal. So I'll start my cycle with 1. Now moving from right to left, we have that 1 goes to 2 in the first cycle, then 2 goes to 3, and then 3 doesn't change in the last one, so 1 goes to 3. Then we'll have 2 goes to 1, then 1 goes to 2, and then 2 goes, oh, I'm sorry, I shouldn't have started with 2 next. I needed to start with 3 because that's the number that we just put down in our cycle. So 3 doesn't change in the first cycle, and then 3 goes to 1 in the second, and then 1 goes to 2 in the third. So we get 1 goes to 3, 3 goes to 2, and then 2 goes to 1, 1 goes to 2, 2 goes back to 1, so 2 goes to 1, and we finish the cycle. And similarly, if we multiply out the last term over here, then we'll get 1, 2, 3. And the point is, this whole thing is a subset of A3. In fact, it's exactly equal to A3, which is what we expect. Now we can do the same thing for multiplying 1, 3 on each side and multiplying 2, 3 on each side, and check this all by hand. Now, of course, this doesn't work super well if we wanted to do this for the alternating group of degree, say, 20, which has a ridiculous number of elements in it. It wouldn't really be reasonable to do it by hand. So let's show that the alternating group of degree n is always a normal subgroup of the symmetric group of degree n by a different argument. So let's show that the alternating group of order n is a normal subgroup of the symmetric group of order n for any n greater than or equal to 2. We want to let A be in Sn, so A is going to be some permutation, and B, or we were using Greek letters for these, so we'll go ahead and do that here. Let's let alpha belong to Sn and beta belong to An. We want to show that alpha, beta, alpha inverse belongs to An. If we can show this for any arbitrary alpha and beta, then that will show that An is a normal subgroup of Sn. So let's look at this. What defines belonging to the alternating group An? Well, it's being able to be written as a product of an even number of transpositions. So we know that beta can be written as an even number of transpositions. Or I should say as the product of an even number of transpositions. So we can have that beta is equal to beta 1, beta 2, up through beta, we'll say 2k, because we know that the number of transpositions that we write beta down as is even, so it's a multiple of 2. Now, we don't know the same thing about alpha. We have no control over the number of transpositions that it takes to write down alpha, but we do know that it can be written as a product of transpositions. So let's let alpha being alpha 1, alpha 2, up through alpha m, say, be a transposition, decomposition of alpha. Now let's look at what we get when we do alpha times beta times alpha inverse. Well, we know that alpha can be written as alpha 1 times alpha 2 up through alpha m. We know that beta can be written as beta 1 up through beta 2k. And then alpha inverse is alpha m inverse down to alpha 1 inverse. And again, as we've seen before, the transpositions, alpha I, are their own inverses, and so we get this. Thus, this means that alpha, beta, alpha inverse can be written as a product of m plus 2k plus m transpositions. But since m plus 2k plus m equals 2m plus 2k is even, because it's a sum of two even numbers, that tells us that alpha beta times alpha inverse belongs to an, because this permutation can be written as the product of an even number of transpositions. Therefore, that tells us that an is a normal subgroup of Sn. So this is how we might do an argument in the case that we aren't going to write things down explicitly. Let's see another we'll see another example in a little bit. But now let's talk about how we actually use this. Why do we bother defining a normal subgroup? And the point is to define groups that have a similar structure to the groups Z mod and Z, which we call factor groups. So the idea behind factor groups is the following. Given a group G and a subgroup H, we won't address the normality here for a second. Remember that we have the cosets AH, where A is any element of G. And the Lagrange's theorem gives us a relationship between the sizes of these cosets and the number of cosets there are and the order of G in the cases that those are finite. And so we have just this collection of sets, this collection of cosets of G. Now, one of the things that we often do in algebra, whenever we have a collection of objects, we want to ask, is there any sort of algebraic structure on them? Is there any way of defining some sort of multiplication or addition on these that makes sense, that gives us a group that we can use to prove things about either the subgroup H or the original group G, something that gives us an insight into what's going on here. So, if we try to define an operation on the set of cosets, then we might try the following. If I have a coset AH and I want to multiply it by a coset BH, the only algebraic structure that we know about so far is the one that comes from the original group G. We, in this sort of abstract setting, know nothing about the specifics of what G are or H are, and we know that G is a group, which means it has an operation that satisfies certain conditions. And so if we want to take two cosets and define some sort of operation on them, well, the only thing that we're going to be able to use is the operation on G. And of course, the operation on G doesn't apply to subsets of G, but to elements of it. So the operation on G tells us that we can do things with A and B, because A and B are elements of G. So we know that using the operation on G, we could get the element AB. So this is the multiplication on G. And we could take that element and look at the coset of H that has that element as a representative. And this is pretty much the only operation that one could actually define here. The only variants basically just come down to this again. We could try slapping inverses on some of these, but that doesn't really change anything. When it comes down to it, this is pretty much the only operation that we could try to define on these elements, these cosets, that has any chance of working. Now, the difficulty here, and the reason why we need the concept of normal subgroups, is that we need to make sure that this is well defined. Now, the thing that could give us problems is, what if we have that A prime is another representative of this subgroup, or of this coset rather, AH? And what if B prime is another element of this coset BH? If we want to try to define the multiplication here, we better make sure that these two are equal. We need to make sure that we need to show that if AH equals A prime H and BH equals B prime H, then ABH, the thing that we would want to define the product of the two things on the left to be, that needs to be the same as A prime B prime H, the thing that we want to define the product of the two things on the right to be. We need to show this condition. In other words, that the operation is well defined. All right, so it's going to turn out, as we'll see in the next theorem, which is going to outline some of our language and notation for this, that the condition that we need in order to make sure that this operation is well defined is precisely that we need H to be a normal subgroup of G. It turns out that is exactly the condition that that gives us what we need. And this is why we care about normal subgroups. They're the ones that allow us to define a group structure on their cosets. So let's look at this. Theorem 66. Let G be a group and H a normal subgroup of G. Pardon me. The set G mod H is the set of all cosets of H, is a group under the operation that we just defined. Under the operation AH times BH is equal to ABH. And it is called the factor group of G by H. When G is an additive group, that is when we are writing the operation as addition rather than multiplication, we write the group G mod H additively, and the operation is given by A plus H plus B plus H, because remember that these are what the cosets of H look like in an additive group, is A plus H and B plus H. These are going to be, the sum of these is going to be the coset A plus B plus H. All right, so we want to prove that this set here is a group. So this notation G mod H with the slash is intended to evoke the intuition of division or fractions. That's not precisely correct. We aren't exactly looking at fractions here, but it's intended to suggest that to our minds. So let's prove that this structure gives us a group. Now, as I mentioned, the first thing that we need to prove is that the operation is well defined. The good news is that once we do prove the operation is well defined, proving the rest of the group axioms hold is going to be pretty much immediately true from the fact that the group axioms hold on G. In fact, if you go back to when we were originally defining the groups Z mod NZ, you'll notice that we went through a very similar process to what we're about to. So comparing the two can be a fruitful exercise. The main difference there is that we were using a different notation. We weren't using the plus H notation that we are here. And we were not doing things in as general a setting. All right, so proof. We show that the operation on G mod H is well defined. Right, so the way that we do this is we suppose that AH equals A prime H and BH equals B prime H. And we wish to show that ABH equals A prime B prime H. All right, so now let's look at what we've got here. Going back to a lot of the things that we noted about cosets of subgroups before, those all still hold because H is a subgroup of G. We have the following. Since AH equals A prime H, we have that A prime belongs to AH, and so there exists an H, an H1 in big H such that A prime is equal to A H1. That's what it means for the two cosets AH and A prime H to be equal. Another way of saying that the two cosets are equal is to say that the two representatives differ by a factor that belongs to the subgroup H. Similarly, there exists H2 in H such that B prime is equal to B times H2. So let's look at what we've got. If we take A prime B prime H, that's the same as AH1 times BH2 H. And we want to show that this is equal to AB times, just AB times H. Well, first of all, notice that H2 belongs to H. And so any element of H, if we look at the coset with that representative, that's just the set back. So the representative, or the coset H2 times big H is just the coset big H back because H2 belongs to H. Now we have the A H1B times H is what we've got. Now here's where we use the fact that H is normal. And it's at this point that the whole process would break down if H were not a normal subgroup of G. We get that AH1 HB is another way of writing that down. And that's because BH and HB are equal. We are also heavily using the fact that the coset construction is associative, meaning that if I've got A, H1, B, H, I can choose to group it up like this, with the B going with the H. And then at this point, I'm going to group it up again, but now like this, with the H1 and the H going together. Now H1 times H is just big H back, because again, H1 belongs to H. And again, we're going to use the fact that H is normal to get that this is A times BH, or ABH. So what we've shown using this process is that it doesn't matter which representative of a coset that we choose. That if we take two cosets and multiply them together, we get a single coset out of it, no matter which representatives we choose. If we choose different representatives to begin with, then we'll get a different representative at the end, but it'll still be a representative of the same coset. So this means that multiplication in G mod H is well defined. All right, so we needed that H was normal to even have multiplication make sense, but once we do know that multiplication makes sense, checking the rest of the group axioms is very fast. So now let's check the group axioms. Number one, we need there to be associativity. So let's let AH, BH, and CH all belong to G mod H, meaning they're all cosets of H. So now, if we have AH times BH and then times CH, well, by definition, AH times BH is AB times H, which gives us AB times C times H. But then by the associativity of G, we have that this is A times BC times H, which equals AH times BCH, which gives us AH times BH times CH. So associativity holds on G mod H. Doesn't matter how you group things up within a multiplication as long as you keep the same order. Let's check for identity. We need to make sure that there is an identity element in G mod H. We claim that H itself, which remember is the coset with representative, the identity, is an identity. For any AH belonging to G mod H, we have that EH times AH is equal to EA times H, but E times any element of G is just that element back, is AH, but of course that's the same as A times the identity times H, which is the same as the coset with representative A times the coset with representative E. So the fact that if we multiply on the left by EH, we get AH, and if we multiply on the right by EH, we get AH back, means we have the identity, means that EH is the identity for the group. Now for inverses, let's let AH belong to G mod H. Now we have that A inverse H is also an element of G mod H. And we have that A inverse H times AH is equal to A inverse A, H, which is the identity, which is the same as A inverse times H, which is AH times A inverse H. So we have that the two elements AH and A inverse H, when you multiply them together in either order, give you the identity element of G mod H. And so this tells us that the inverse of AH in the group G mod H is equal to A inverse H. So that means that G mod H has inverses. And that's it. That takes care of things. Now I want to talk briefly about something that becomes fairly clear when we're looking at this argument in particular right here. We didn't have to do really anything in order to prove that the factor group G mod H is in fact a group. Once we have the well-definedness, that was something we needed to do. But once we know that we even can define the multiplication, associativity of the factor group just comes from associativity of the group. The identity element of the factor group is simply the element of the factor group that has a representative of the identity from the group. And the inverse elements in the factor group are just the elements corresponding to the inverses of the representatives. And so the factor groups, it's important to remember that the factor groups are not actually introducing anything new to the structure. They're not adding in any new elements that we have to somehow make sure are interacting properly with the elements of G. In fact, the factor group loses information. What the factor group does is it identifies elements together that were distinct in the original group G. In the original group G, two elements might be considered to be the same in the factor group because they belong to the same coset of H. We'll look at some examples here in a second, but it's important to note that the factor groups really do lose information. They're identifying things together in the group G and treating them as the same. So it's collapsing the group down into, in some ways, a simpler structure, or at least a smaller one than the group G before. It's not actually adding in anything new. Now, that's not to say that it's not useful. Factor groups are incredibly useful, partly because sometimes the original group is just too hard to understand. Sometimes we understand a group by taking some of its factor groups and studying them because they're smaller and they're easier to understand. Sometimes we have a group that we're trying to understand and we can study it by comparing it to the factor group of some other group that we know very well. Factor groups are very, very important. But the proper way to think about them is as a collapsing of the original larger group G. All right, so let's look at some examples. And the first one that I want to look at are the groups Z mod NZ that we looked at way back at the beginning of the semester. So let's look at an example. So first of all, since the group G is abelian, this means that every subgroup of Z is normal. This means that when we're looking at an abelian group, we can form a factor group with any subgroup because all subgroups of an abelian group are normal. Furthermore, since Z is cyclic, it's generated by 1 or negative 1, every subgroup is cyclic. We had that when we were looking at cyclic groups. So that means that every subgroup of Z is of the form the cyclic group generated by n, where n is some element of the integers. So that'll be 0, n, 2n, 3n, etc. And then negative n, negative 2n, etc. back this way. We also called this set NZ, which also works. So every subgroup of Z is of the form here. So that means that every factor group of Z is of the form Z mod, the cyclic group generated by n, or in other words, Z mod NZ. Now, we had written the elements of this group before as 0 bar, 1 bar, 2 bar, etc. up to n minus 1 bar. And we could also write these down using the notation from the previous theorem. We could also write these down as 0 plus nz, 1 plus nz, 2 plus nz, and so forth and so on, up through n minus 1 plus nz. We could also have written the group this way. So the notation that we had before, the Z mod NZ, really was used because the groups that we're looking at there are truly factor groups. They're factor groups that we were using a slightly more efficient notation for, but they are in fact simply factor groups. And we can look at a lot of things about this and express all the relationships that we did before in terms of some of this new language. So for instance, we have that A plus NZ is equal to B plus NZ if and only if B is in A plus NZ. Or in other words, A and B differ by a multiple of n. So the factor group idea really is just coming from generalizing this notion of the Z mod NZ, sometimes called the modular arithmetic. It's important to note that historically, the Z mod NZ groups definitely came first. These ones have been known about for a very long time, long before abstract algebra became sort of codified and recognized as its own thing. So the factor groups really are a generalization of the Z mod NZ groups. All right, let's look at a non-abelian situation. So let's let G be the group GL2R. And remember, this is the set of 2 by 2 matrices where each of the entries are real numbers and the determinant is non-zero. Or in other words, it's the set of invertible 2 by 2 matrices. We have that G is a group under matrix multiplication. Now let's let H be the group SL2R. This is called the special linear group, and it's the set of all matrices, all 2 by 2 matrices with elements from R where the determinant is exactly equal to 1. So now we have that H is certainly a subgroup of G. A subset of G. Also, as it turns out, H is a subgroup of G. Let's take that for granted, but let's show that H is a normal subgroup of G. So, for this, let's let little h belong to H and little a belong to G. Now, remember that even though I'm using single symbols for these, H is in fact a 2 by 2 matrix, A is in fact a 2 by 2 matrix, and the operation here is matrix multiplication. We wish to show that A inverse belongs to H. Now, capital H is the set of all matrices with determinant 1. And so if we want to show that the matrix A inverse belongs to H, we are going to need to show that it has determinant 1. So now, using some linear algebra, we have that the determinant of the matrix A inverse, it turns out that the determinant of a product of matrices is the product of the determinants. So we have that the determinant of A inverse is the determinant of A times the determinant of H times the determinant of A inverse. Well, we know that the determinant of H is 1, and that's because little h comes from big H. And furthermore, we have that the determinant of the inverse of a matrix is the inverse of the determinant of the original. So the determinant of A inverse is the reciprocal of the determinant of A. So we get that the determinant of AHA inverse is the determinant of A times 1 times the inverse of the determinant of A, which of course is just 1. So that means that AHA inverse belongs to H. So that means that H is a normal subgroup of G. All right, that means that we can form the group G mod H. So then what does it mean for two cosets of this subgroup H to be equal? That'll give us some idea as to what this group G mod H is supposed to be measuring. So now we have that AH equals BH. Remember, this occurs if and only if A inverse B belongs to H. We had this back when we were looking at cosets of groups. I.e., if the determinant of A inverse times the determinant of B equals 1. That is the determinant of A inverse B, which is the determinant of A inverse times the determinant of B is 1. And that occurs if and only if the determinant of A equals the determinant of B. So what this is saying is that in the factor group G mod H, the only thing that distinguishes two matrices are their determinants. If two matrices have the same determinant in G, then they go to the same coset. They are representatives of the same coset in the group G mod H. So this, in fact, is saying that the group G mod H forgets everything about the elements of G except their determinant. And so the group G mod H has really a far simpler structure than the group G does, because it really doesn't tell the difference between two matrices unless they have different determinants. What we're going to see in a later section is that we can make this very explicit. It turns out that the group G mod H, because it basically turns every matrix into just its determinant, that the group G mod H has the same structure, the same algebraic structure as just the set of non-zero real numbers under multiplication. We are going to be able to say that it's isomorphic to that, but we'll get to that. We'll get to that a little bit later. For now, we see that H is a normal subgroup of G, and so we can, in fact, form the group G mod H. All right, quick remark. Lagrange's theorem can be stated more efficiently when the subgroup H we're looking at is a normal subgroup of G. Remember that Lagrange's theorem, the standard form of it, says that the index of H in G is equal to the order of G divided by the order of H, if these are all finite. But we also have that the index of H in G, this is equal to the number of cosets of H in G. But that's, of course, exactly the same as the order of the group G mod H, because the elements of the group G mod H are exactly the cosets of H in G. So in this case, we can write that the order of the group G mod H is equal to the order of the group G divided by the order of the group H. And this is a very nice way of seeing things. When we write things down this way, and we think of the slash for the factor groups as being similar to division, and if we think of the order notation being similar to absolute value notation for real numbers, then this equation is exactly the same as the equation that we get for real numbers. The absolute value of a quotient is the same as the quotient of the absolute values. Now, we don't state Lagrange's theorem this way because this symbol, G mod H, is only defined when H is a normal subgroup. If H is not a normal subgroup, we do not even attempt to define what that notation means. And that's why instead we have the notation of the index of H in G, which is perfectly well defined, even when G mod H isn't a group. Okay, there are a couple of applications of factor groups that we want to talk about. Theorem 67, for instance, says let G be a group, and if G mod the center of G is cyclic, then G is abelian. Now remember that if G is abelian, then the center of G is in fact all of G itself, because if G is abelian, then everything commutes with everything else. And so this is saying something weaker. It says if G mod the center, maybe we don't know that the center is all of G, but we know that the factor group G mod ZG is cyclic. It has a pretty simple structure. Well, it turns out that that's enough to prove that the center is actually equal to all of G. In particular, what this shows is that it's impossible for G mod ZG to be a non-trivial cyclic group. If G mod ZG is cyclic, then in fact it only has it's the group of size 1. It's the single group of order 1. Let me come back to that and talk about that briefly after the proof. All right, so let's suppose that G mod ZG is cyclic with generator A ZG. Now, any element of G mod CG is of the form some element of G times ZG. They're cosets of Z of G. They're cosets of the center. So now we want to say let B belong to G. There exists some I such that B times ZG, which is an element of the group G mod ZG, that's going to be some power of the generator. That's what it means for G mod ZG to be cyclic. It means that any element of it can be written as a power of one of the generators. In this case, the generator is A times ZG. Now, the powers of a coset are just the coset of the powers. So this is just AI times ZG. Therefore, this means that B belongs to AI ZG. So there exists some little z inside Z of G such that B is equal to AI times Z. Therefore, we have that AB is equal to A times AIZ, which is A to the I plus 1Z, which is A to the I AZ. Now, we know that Z is an element of the center, which means it commutes with everything. So in particular, if we have AZ, we can write that as ZA. But now, AI times Z is just B. So, by running through this equation and using the fact in the second to last equality that Z commutes with everything, we have that AB equals BA. So, that means that AB equals BA. Now, B was arbitrary. We just let B be any element of G. This means that A and A commutes with it. That means that A belongs to the center. So that means that G mod ZG is generated by A times ZG, which is just ZG itself, or in other words, it's the identity. So a group that's a cyclic group generated by the identity element is just has a single element in it. So that means that G mod ZG has just a single set in it, just a single set ZG. And therefore, this means that for any B in G, B times ZG equals ZG. So B is in ZG. Thus, this tells us that G is equal to ZG, which means that G is abelian. All right, so we showed basically that we're using essentially the fact here that all cyclic groups are abelian. We could perhaps look at a more complicated theorem which involves the factor groups being abelian, or the factor group by the center being abelian, telling you that the original group itself is abelian. We're going to start here with the cyclic groups. And so what we see here is that by looking at the structure that exists in the factor group, if the factor group has a particular structure, like being cyclic, then that tells us something about the original group, which is a typical example of how we use factor groups to do that. All right, I now want to come back to the thing that I mentioned at the beginning, which has to do with this last part of the argument that we have down here. And I want to talk about generally how we use the factor groups being trivial or not. So let's recall that the trivial group, or perhaps a trivial group, is the group which is the singleton E containing one element, where that element is itself the identity, also its own inverse, and it's the trivial group. It's the simplest possible group. Now, the fact that we will use, or that we did use in the previous problem, that we'll use occasionally, that is the fact that if G is a group and H is a normal subgroup of G, then G mod H is the trivial group G if and only if G is equal to H. And this is not terribly hard to see, but it's an important fact to keep in mind. So let's see how this goes. Sorry, I should have written this slightly differently. That G mod H is the singleton set EH, if and only if G is actually equal to H. So let's see how that goes. So if G mod H is actually equal to the set EH and it has only one element in it, this tells us that the only coset of H in G is EH, which of course is just equal to H. So if A is any element of G, then that means that AH, which is a coset of H, has to actually be equal to H, so A has to belong to H. Because every element of G belongs to some coset of H, and if the only coset of H that exists is H itself, then that means that every element of the group has to belong to H, which tells us that H actually has to equal G, because we know it can't be any bigger. H is a subset of G. And then a similar argument goes the other way. If G is equal to H, then given any element A of G, or A belongs to H, so that means that the coset AH is just H itself. So that means that the set of cosets of H is simply the set H. So we're going to use this fairly often. If you've got a normal subgroup H and you know it's not the whole group, then you know the factor group has to have more than one element in it, because it's got all the cosets of H in it. And if you know that the factor group G mod H has more than one element in it, then that means that H wasn't the whole group to begin with, and vice versa. So this is not a terribly deep statement, but it's one we're going to use very, very often, so I wanted to emphasize it. All right, now I want to do a slightly more advanced application, which is actually going to be very, very important to our classification of finite abelian groups. So let's look at Theorem 68. Let's let G be a finite abelian group, and let P be a prime divisor of the order of G. Under these conditions, G has an element of order P. This is one of the first or this is only the second theorem we've ever had that guarantees us the existence of an element with a particular order. And the previous theorem that we had only applied to cyclic groups, which is a very, very narrow category of groups. This is talking about any finite abelian group, which is much, much broader. And this is saying something that on the face of it should be a little surprising. If I've got some group G, and let's say that it has order 120, I've got some abelian group, it's got 120 elements in it, well, then I know that 24 is a, I'm sorry, not 24, I need a prime. I know that 5 is a divisor of 120. 5 is a prime divisor of 120. What this says is that given any abelian group of order 120, there always exists an element of order 5. And this was at least surprising to me the first time I encountered it. Surprising that we can always guarantee that there exists an element of a given order. And this applies to all of the divisors of the order of G. So let's see how we go about this. And we're actually going to attack it using factor groups, which, again, it doesn't look like we necessarily will. There are no factor groups in the theorem. What the factor group is going to allow us to do is to use induction. It's because the factor group is going to be smaller than the original group, unless the original subgroup was trivial. Because the factor groups are smaller, we're going to be able to use induction to attack this problem. So let's look at the proof. Let's let E be, sorry, don't need that. Let's just jump to, we proceed by induction on the order of G. So what's the base case here? The base case is actually 2. The base case is actually the order of G being 2. And the reason for that is that if the order of G is 1, then there are no prime divisors of it. So our base case is the order of G being 2. If the order of G is 2, then the non-identity element A must be its own inverse. So that means that A squared is equal to the identity, hence the order of A is 2. Hence the order of A is 2, and 2 is the only prime divisor of the order of G. So if the order of G is 2, then its only prime divisor is 2 itself, and there is an element in G of order 2. You just take the only non-identity element in the group. All right, so now let's move on. So now let's suppose that the order of G is greater than 2, and that the result is known for groups of order less than the order of G. So we're using strong induction here, where we're assuming that we know the result for groups of all order less than the order of G. So now let's just let A be any element of G other than the identity. And let the order of A be Qn for some prime number Q. Because the order of A is not 1, that means that the order of A is divisible by some prime number. Let's just let Q be one of those prime numbers. If Q equals P, then we have that the order of A to the n, which is Q, is also P, so we're done. So this is because we have that A to the nq is equal to the identity, which means that A to the n to the qth is the identity. And if there were any number smaller than q that you could put in that exponent to get the identity, then that would mean that the order of A was not nq. So if q is equal to p, then the order of an is equal to q, which is p. So we're done because the element an satisfies the conditions of the theorem. So now let's suppose that q is not equal to p. So we don't get the easy win. So let's let I want to let G prime be the factor group G mod, the cyclic group generated by A to the n. So let's see what we've got with this. Lagrange's theorem will tell us about the order of G prime. So by Lagrange's theorem, the order of G prime is going to be equal to the order of G divided by the order of A to the n, which is the order of G divided by Q. So this means that the order of G prime is less than the order of G, because it's the order of G divided by some prime number. And furthermore, P still divides the order of G prime. We know this because we know that the prime number P divides the order of G, and Q is a prime number which is not P. So if we take the number order of G, it's divisible by P, we divide it by some prime number Q, then the new result that we get is still going to be divisible by P. So we have this. And now we can use induction. So by the inductive hypothesis, there exists some element B, let's see, B times cyclic group AN in G prime with order P. So here we're using the inductive hypothesis, which says that if I take any group with order less than the order of G, then the theorem statement applies. In particular, that means that since P divides the order of G prime, there exists some element of G prime with order P. Now, all the elements of G prime look like B times the cyclic subgroup AN, where B is an element from G. All right, we're going to use this element in order to find our element in G with order P. Okay, so now we have that the order of B times the group AN, the cyclic subgroup generated by AN, has order P. So that means that the order of AN, which is the identity element inside G prime, is equal to B times the cyclic subgroup AN raised to the pth power, which of course is b to the p times the cyclic subgroup AN. Therefore, this tells us that b to the p belongs to the cyclic subgroup generated by AN. We're sort of coming back out of the group G prime and back up onto the level of the group G again. We've taken the properties that we needed to out of G prime, the fact that this element B times the subgroup generated by AN has order P, and saying, all right, well, what does that mean when we lift back up to the level of the original group G? And what it means is that we have some element B, which is whose pth power belongs to the cyclic subgroup generated by AN. Now, if b to the p is actually equal to the identity, then we're done again. Since that would tell us that the order of b is equal to p. Now this is because p is a prime number, which means that let me put in a couple more details like that. So if the order, if b to the p is equal to e, is equal to the identity, then that means that the order of b divides p, and since the order of, and since b is not equal to the identity, that tells us that the order of b is not equal to 1. So the order of b divides the prime number p, and it's not equal to 1. Hence, the order of b equals p, and we're done. So let's suppose that b to the p is not equal to the identity. Since b to the p belongs to the cyclic subgroup generated by AN, and the order of AN is equal to Q. We saw that before. We have that b to the PQ is the identity. Thus, we have that b to the Q to the P is the identity. So now we have an element b to the Q, which when you raise it to the pth power gives you the identity. So that tells us that the order of b to the Q divides p. If the order of b to the Q equals 1, then that means that b to the Q is the identity. So this means that, again, dropping back down to the group G prime, if we look at the element b times cyclic subgroup AN in B prime, and we raise this to the qth power, this is b to the Q times the cyclic subgroup generated by AN, which would be the identity generated by AN, which is, or times the group generated by AN, which is the group generated by AN, which is the identity inside G prime. So hence, that would tell us that the order of B, AN divides Q. But we have that the order of B times the cyclic subgroup generated by AN is P. So that means that P divides Q, a contradiction, because P and Q are two distinct prime numbers. So that tells us that the order of B to the Q can't be 1. So the order of B to the Q is not equal to 1, but we have that the order of B to the Q has to divide the prime number P. So that means that the order of B to the Q has to actually equal P, and so B to the Q satisfies the theorem. By induction, the theorem holds for all orders of the group G. So this was a reasonably complex argument where, in order to understand the order of the element B, first of all, we had to we started up in the group G, and we looked at the element A. We basically just chose a random element A, and we said, does this have the order that we want? If so, great. If not, let's quotient by it. That moves us down into a smaller group where we could use the inductive hypothesis and understand things there and get an element with representative B down below. Then we could say, all right, well, we know this element B times the subgroup generated by AN has order P. What does that say back on the level of the group G? So we moved back up, figured out what that meant about B, and then we needed to prove one more thing. We needed to prove that the order of B to the Q wasn't 1, and so we assumed it was, moved back down to the group G prime, proved that we get a contradiction, and that finished the argument. Being able to move back and forth between thinking about elements of the group G and elements of the group G prime, which are cosets with representatives from G, is an important technique when working with factor groups like this.